This time, let's talk about the solution for an nth order homogeneous differential equation if the roots of an auxiliary equation are actually imaginary and some of them has multiplicity more than 1. Okay? So let's talk about the solution, and the solution will actually written in this manner. Y is equal to e to the power of ax. Take note that if we talk about imaginary roots, we have any root with a plus minus bi. A is your real part of your complex number, and your b is the imaginary part of your complex number. So you have your a times c sub 1 cosine bx plus c sub 2 sine of bx. That is for it's if the roots are imaginary but no repetition. But if it repeats, meaning this root has multiplicity more than 1, so you will be adding here another e to the power of your ax as well. But we have here another component x, or if you would like to, you're going to write it in this manner, plus x e to the power of ax, okay? And then you will have here times c sub 3 now, cosine of the same bx, plus c sub 4 sine of your bx. And if it repeats again, it will be like this, x squared e to the power of ax still, okay? And then you will have here c sub 5 cosine of bx plus c sub 6 sine of bx here. So what will happen if there are infinitely many? So plus dot 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 plus you have x to the power of n minus 1. Then you have here times, you're going to multiply this by e to the power of the same a. You will have here c, since it has a lot of c, n plus 1 cosine of bx still, plus cn plus 2, another constant, sine of bx. As you can see, it has a lot of forms. It is actually patterned to the solution when we have repeated real roots. I'm going to return to that one. When you say repeated real roots, it's actually expressed in this manner, e to the power of mx, right? Times, you will have here c sub 1 plus c sub 2x plus dot dot dot, plus you will have here c sub n, and you have x to the power of n minus 1. Okay, this is situation. However, okay, take note that if we have imaginary roots, this becomes a, and this component here will be a component of a trigonometric ratio cosine and sine. That's why we'll be breaking that into two parts. This as well, breaking into two parts with x, and breaking this into two parts with x minus 1, so similar to that. I'm not going to show you the derivation here, but it follows the same concept as to that. Now, let's say, some sort of example, we'll have some examples later on, but say we have roots here. Let's say our m is equal to 6 plus minus 3i. And let's say we have multiplicity of 2, okay? Meaning there are two different, we solve the auxiliary equation, but we have shown that this has multiplicity of 2. So we're going to use here the solution y is equal to, so we're going to write it this manner. Multiplicity of 2 means we're going to end up here. So we have e to the power of, by the way, before we forgot here, our a is 6 and our b is 3. So we have here 6x times c sub 1 cosine of 3x plus c sub 2 sine of 3x. That's for the solution if it doesn't repeat. But if it repeats, just like here, multiplicity of 2, so we're going here plus x again, e to the power of 6x. In this time, we're going to use here c sub 3 cosine of 3x plus we have here c sub 4 sine of 3x. We're using different constants because this is a result with this, and we have a variable x for that. This is the solution for this example. I'm not going to give an example for combinations, but you can imagine if our roots are actually imaginary. Our roots are imaginary with multiplicity, and let's say another root. Let's say in this case m sub, we have 1, 2, 3, 4. Let's say m sub 5 is negative 4, and let's say m sub 6 is 2, and m sub 7 is also another 2. So we have multiplicity for real, and we have a distinct one here. So it could be a combination for all. Okay, so you can try that on your own. Allow me to erase this so that you will not be confused. But this is how we write the solution, okay, for situation like this. Thank you very much for watching.